This PowerPoint is about acid-base titrations, and the first half of the PowerPoint we'll be talking about titration of a strong acid, which is pretty simple and straightforward, and the second half of the PowerPoint will be talking about titration of a weak acid, which is quite a bit more complex. But a titration in general is a procedure set up to determine the concentration of some substance. And so, for example, let's say you have an acidic substance, could be a water sample you collected from a creek, and you just need to know what is the concentration of acid in there. And so you typically would set up a burette with a known concentration of a base. And by monitoring how much of the known concentration of base it takes to neutralize the unknown concentration of acid, you can use stoichiometry to find out what this concentration is. And so the unknown substance is called the analyte, and the known concentration of substance is called the titrant. Typically what people will do as they're titrating is they will make a pH curve, and so they'll monitor the volume of base that they add from the burette, and so the units might be milliliters on the x-axis and versus the pH of the solution that's being titrated. So obviously if you're titrating an acid, the pH before you start adding any base is going to be quite low. And as you add base, the pH is going to increase. When there is a very sudden jump in pH of a couple of units, we call that the equivalence point. And that's the equivalence point is when, well, mathematically, it's when the moles of acid equal the moles of base that have been titrated. So students get this confused with the halfway point. So what I want you to keep aware of or jot down that the equivalence point is when all of the acid has been neutralized. It's the end of the reaction when all the acid has been neutralized. And so really, to make this equation better, it should have been the moles of acid to begin with equal the moles of base added. Okay, so they've neutralized each other. So this first half of the PowerPoint, we're going to be talking about titration of a strong acid, like hydrochloric acid, for example. And at the equivalence point, when you've titrated or neutralized it all, just as you would expect, the pH is 0. Not 0, the pH is 7. Okay, neutral, once you have completely neutralized. So if you look at the reaction for titration of a strong acid, at the end, at the equivalence point, okay, the original acid is going to be gone. The base and the acid have neutralized each other, and all you will have left is some innocuous ionic compound and water. All right, so we can use, now I want you to listen really carefully to this slide, okay? Because this equation is misused very commonly by students. This is a version of the dilution formula, okay? So the dilution formula, if you add 2 or more solutions together, you can start with the original concentration of the solution and find the diluted concentration with this formula. At the equivalence point, and again, only at the equivalence point, can you use a version of the dilution formula. Now, what's really important and what students will often leave out are these little coefficients on each side of the equation. You cannot leave these out. these account for the mole ratio of the acid that is being titrated and the base that is being used to titrate with. So, for example, if you're analyzing a diprotic acid with a mono sodium hydroxide, what these little coefficients stand for, M, now this is a little tricky, so you're going to have to pay attention. M is the number of hydrogen ions, acidic hydrogen ions, per 1 molecule of acid. So let's make sure we understand that. If it was HCl, M would be 1 because there's 1 acidic hydrogen per 1 molecule of acid. If we had H2SO4, M would be 2. There are 2 acidic hydrogens per 1 molecule, okay? Same thing with the base. So Ma, of course, refers to the acid, Mb refers to the base. So NaOH, as far as the base goes, N would be 1, because there's 1 OH. If you had something like barium hydroxide, N would be 2. Okay, so if you leave these things out, you're totally ignoring the mole ratio. All right, so here's a sample calculation. This would be a very simple multiple choice calculation, but very easy one to miss if you don't remember your M and N's for this equation. All right, so what do we have? As far as the acid side, we know that there's only 1 acidic hydrogen. We're trying to solve for the concentration of the acid, and oh, here we go. I got caught up for a minute. Yeah, proves you got to read carefully. And there are 50 milliliters of the acid. Barium hydroxide, there are 2 hydroxides per 1 molecule, and we have 30 milliliters of barium hydroxide and its molarity. So just do your algebra math, isolate the molarity of the unknown acid, crunch the numbers, and you get that the molarity of the acid you are titrating is 0.12 molar. I want to emphasize again that this equation only works at the equivalence point, only works when you're done with the titration. It does not work partway through any titration. If you are doing a titration, you need some way to know when the equivalence point is being reached. So if you are using a pH meter that is immersed in your analyte solution, you can record the pH directly. Not everyone has a pH meter, and so in that case, you would use what we call a color indicator. So where it says AB indicator, it's really color indicator. So basically, you choose a substance that changes colors at the pH at which you expect to reach the equivalence point. So remember I said in the beginning, if you are titrating a strong acid, the pH at the equivalence point will always be 7. Okay, so if you did not have a pH meter, what you would want to do is you would want to find a substance that changes color right at a pH of 7. All right, so I would say any of these would be okay. Yeah, any of these would be fine. Let's talk about a titration curve again for a moment. So pH, you should be able to just briefly sketch the shape and the key features of a titration curve. So know that the pH is on the y-axis and milliliters of base added is on the x-axis. And if you were just shown a rough graph, for example, and asked to label key parts, you would first identify the equivalence point. So you look for this sharp rise in pH, measure halfway up that rise, and then go over to the y-axis, and that tells you the pH at the equivalence point. So if the pH at the equivalence point is 7, that means that it is a strong acid that is being titrated. Okay, before you add any sodium hydroxide, it's just the pH of the acid by itself. So this solution of acid has on its own, before you start titrating, has a pH of about 1. All right, so again, if you don't have a pH meter, and you typically want to put an indicator in this case, they're just showing the example of either phenolphthalein or methyl red. And phenolphthalein, for example, will be clear, colorless, I should say, not clear. It'll be colorless as long as there are acidic conditions, and then it turns pink as soon as it gets it all basic. So as soon as you pass pH of 7, that bugger's going to light up pink. Alrighty, so if you have to calculate the concentration of hydronium ion rather than having a pH meter, which is so much easier, then I just want to remind you the formula for pH, minus log of the concentration of hydronium ion. Now, listen really carefully. This is another stage it's really, really important to know, okay? We're still talking about titrations of strong acids. So, for example, hydrochloric acid. If I had an 0.1 molar solution of hydrochloric acid and I asked you what the pH is, would you be able to get that? Okay, so if not, this is my kind of drill again. It's time to start reviewing for the final, guys. So what is the definition of a strong acid? The definition is that in water, strong acids 100% dissociate into the individual ions. You need to be able to know that and draw this type of dissociation reaction. So that means in water, if it's a strong acid, that intact molecular structure is gone, and you have 100% the individual ions. So pH, finding pH of a strong acid is very easy because hydronium ion concentration, which is what you need to calculate pH, equals the original concentration of the acid. So if you had 0.1 molar HCl to begin with, that means you're going to end up with 0.1 molar hydronium ion. Alrighty. So let's go ahead and do an example, titration of a strong acid. Now be aware on a test, it's unlikely that you're going to be told whether or not the acid that's being titrated is weak or strong. So again, I would do that right now today. I would print out or make a list of the strong acids and strong bases so that you can identify it for all sorts of questions. So what are we titrating here? We have 50 milliliters of a 0.1 molar solution hydrochloric acid. Obviously, it's not an unknown in this problem. And we are titrating it with 0.1 molar sodium hydroxide. Now, the first thing I do in any type of titration is I look at the relative concentrations of base and acid. The easiest type of problem is when the concentrations equal each other. The reason that will help you is if the concentrations of acid base are equal and they're both M and N, those little coefficients, are both 1. So this only has one acidic hydrogen, the base only has one hydroxy group. That means that you'll know right away when will the equivalence point be added. The equivalent, or when will it be reached? The equivalence point will be reached when you have added the same number of moles of base to acid. And you can do that easily since the concentrations are the same, the volumes must be the same. So if that didn't make sense, it will as we go along. So here's a basic stepwise for a titration. First, write out your balanced neutralization reaction. What's going on here? So this is good practice for the final again. It's very simple. It's an acid-base reaction. Okay, what do you get? Acid-base, you always get, if it's a strong acid and strong base, you always get water and then the salt. Ionic compound. All right, and everything's 1 to 1 to 1 to 1. All right, calculate moles of acid and base. So remember, if you have solution, the way to calculate moles is molarity times volume. And so in a titration, you'll always have molarity and volume. So you just multiply these by each other to get moles. Again, you got to do stoichiometry, but you've got to keep mole ratio in mind. Anytime you have a chemical reaction, you need to account for mole ratio. Now, if it's just a dilution, there's no reaction and you don't have to worry about mole ratio. All right, so once you have multiplied molarity times liter and you have moles of each the acid and the base, how do you get concentration of the acid? Because remember, to get pH, we don't just need moles of the acid at some point in the titration, moles left. We need concentration to get pH. So you would just take the moles that you've calculated and divide it by the total volume of the solution. Now remember, if you're titrating, you've got a container of, let's say, acid down here, and your burette, you're adding base, and so your volume is changing constantly during a titration. And so if you're asked to calculate the pH at various stages of a titration, the total volume is going to change constantly. So I'm going to go ahead and work each of these problems individually. They may seem somewhat complex, but it's definitely worth taking your time. Make sure you understand all of them. And then I would recommend, before going on to titration of a weak acid, that you work some strong acid titrations in the worksheet I've provided. All right, so there were four or five problems in one. If you go back and read that, it asked what the pH was before the titration even begins, after you've added 25 milliliters of sodium hydroxide, 50 milliliters, and then 60 milliliters. So before the addition of any titrant, so what we have in the beginning is a solution of 0.1 molar HCl. And if it says before the titration begins, there's no sodium hydroxide in there. So all you have to do is take minus log of the concentration of that. If it's a strong acid, that's it. That's all you have to do. So the pH in the beginning is 1. Yeah, and for some reason, a lot of students, if the problem says before addition, then it's not a chemical reaction. It's just a pH calculation problem, so just be aware of that. After addition of 25 milliliters of sodium hydroxide, now you have a reaction. And your reaction, of course, the acid plus the base you're adding. And for the stoichiometry, you don't need to know the products. I'll write them out for you just so you can hopefully grasp what's going on better. But when you're trying to calculate pH, all you care about really is how the concentration of HCl is changing and how much NaOH you've added. So let's look at this. It kind of looks like an ice table. You don't have to set it up in table form. If you are more comfortable doing these calculations just kind of longhand, that's fine. But the bottom line is, for each pH calculation, you need to figure out what how many moles of HCl you have left, how much you've neutralized, and then the moles of sodium hydroxide added. So again, to find moles, you are going to be multiplying volume times molarity. So you might have to go back to the original problem and see what those are. We started with 50 milliliters of HCl. Its concentration was 0.1 molar. So we started, okay, before the reaction started, we started with 0.005 moles of HCl. In this problem, we've added 25 milliliters of sodium hydroxide. It had the same concentration as the acid, so we have added 0.0025 moles of sodium hydroxide. So since you're dealing with a strong acid and a strong base, they're going to completely react. It's not going to be a partial reaction or an equilibrium. It's going to full out react. So all of the base that you add, all of the strong base you add is going to react. That's why I have minus here. And you're going to end up with no sodium hydroxide left. It's all going to react. So however many moles of sodium hydroxide you have reacts with the acid. So you subtract that many moles out. And in this case, you have 0.0025 moles of the HCl left that is untitrated. So this is the halfway point, right? You started with 50 moles of acid and you only have 25 moles left. So you're at the halfway point. So bottom line is, what is the pH though? So as always, use the formula for pH. Now, concentration of hydronium ion. We have the moles of acid, but we need molarity to get the pH. So how do we get molarity? It is moles divided by, and this is where you have to be a little careful during a titration, divided by the total volume. What is the total volume? Well, you've got to go back and figure out, okay, we had 50 milliliters of the acid, and so far we've added 25 milliliters of the base. So our total volume is, at this point, 75 milliliters. And so that's how we find molarity, and then we can easily get pH. So pH in the very beginning was 1. Since you're adding base, you expect pH to go up, and it has. When we're at the halfway point, it's gone from 1 to 1.48. Moving on in our titration of a strong acid, the third question said, what is the pH after the addition of 50 milliliters of NaOH? Now, at this point, we have added the same number of moles of NaOH as we originally had of the acid. And when that happens, we are at the equivalence point. And since it's a strong acid, we expect the pH at the equivalence point to be 7. All right, so if you identify that you're at the equivalence point, if you can just quickly see that in your head, and you know it's a strong acid, you don't have to do any calculation unless you're asked to. You can just say right away, okay, I'm at the equivalence point, pH is 7, I'm done. But just to show you the calculation, again, the moles of acid we started with, 0.005. The moles of base, after we've added 50 milliliters of base, are the same, 0.005. And so the acid we're going to have left after this much base is added is 0, and we're going to have 0 base left, because where are we? If you were at the equivalence point, all of the original strong acid and strong base are gone. These are all gone at the equivalence point, and all you have is product at the equivalence point. All right, and these products, neither of these is capable of changing the pH. So the pH is 7, as always, for a strong acid. Now, occasionally, not nearly as often, but occasionally you will get a problem that asks you, or that actually adds too much of the titrant, the base in this case. And so the pH is not going to be 7. If you shoot past the equivalence point, the pH is going to be greater than 7 for strong acid. So Just so that in case you see that, this is what you do. Again, start by calculating the moles of each. Now, all 0.006 moles of the base cannot react because the limiting reactant is switched, okay? Now we have less of the acid, okay? So the maximum amount of base that can react is 0.005 moles. So all the acid's going to get neutralized. It's going to be gone, but you are going to have excess NaOH because you added too much. So how do we find the pH of this now? Well, it's not going to be 7 anymore like it is at the equivalence point. It's going to be greater than 7. So let's see how we do that. Since all we have is sodium hydroxide is a strong base. So it'd be perfectly fine to say we have 0.0010 moles of hydroxide. That sodium is just a spectator. And so it's a couple-step process to find pH. I would find pOH first, because that's what we're dealing with, minus log of hydroxide concentration. So again, you can't stop at moles. You've got to get molarity. So we have moles divided by total volume. So you've got to go back up to the problem to see what the total volume is, okay? So far in there, we have 50 milliliters of the acid and 60 milliliters of the base. And so the total volume is 0.110, I think, right? And so pOH is 204. Make sure you don't stop there. Then pH, again, pH is, if you hear breathing, that is my dog, not me. So pH is then 14 minus pOH. And as you would expect, if you've added excess base, your pH should be greater than 7. We're going to start talking about titration of a weak acid now. It's quite a bit more complex than titration of a strong acid, so make sure you listen to this portion of the PowerPoint when you are alert, have patience, and focus. We're going to start out by comparing the titration curves of a strong acid to a weak acid and look at the key differences. This is a very common multiple choice question to show you multiple pH curves and ask you to identify what type of acid each curve represents. So as you might expect, typically the initial pH before you've added any base for a strong acid is lower. It's more acidic, stronger acid than the initial pH for a weak acid. The second thing is you tend to kind of have more of a flat line here when you're titrating strong acid. The pH increases quite slowly. For a weak acid, you have more of kind of just a mild lump here. This is called the buffer region if you're dealing with a weak acid. Probably, well, there are two most apparent differences. One is that the equivalence point for a strong acid is sharper, more pronounced, and the equivalence point for a weak acid is more vague, okay, more gradual. So if we, let me erase all that. So you should be able to find the equivalence point from a titration graph. And so let's look at that. So as always, you want to find the halfway point between this sharp rise in pH. And so roughly for the strong acid, the pH at the equivalence point, as expected, is 7. So if you're shown a titration graph and you determine the pH at the equivalence point is 7, you know right away that is titration of a strong acid. Let's do the same for the weak acid. All right, so the blue is the weak acid, and so let's estimate the halfway point there. So titration of a weak acid, this is something worth writing down and remembering. titration of a weak acid, the equivalence point for titration of a weak acid is always, the pH is always greater than 7. Always. And we'll go into why that is later, but for right now, just make sure you know that. If I just had to make a sweeping statement, I'd say the pH at the equivalence point for a weak acid is usually between 8 and 9. Okay, it goes outside of that, but that's what I see most often. Let's talk about why the pH at the equivalence point for a weak acid is greater than 7. Why is that? Let's write out the generic acid-base equation that represents while we're titrating a weak acid with a base. So as all acid-base reactions, and you can imagine, I mean, you've got some type of countercation. I've just left it out because it's a spectator. All right, so the product, just for comparison to ground you, if we're titrating a strong acid or strong base, the salt product might be sodium chloride, for example, right? Because chloride comes from a strong acid, HCl. This chloride cannot change the pH of water, okay? It'll just sit there as a spectator. However, if you start with a weak acid, so instead of HCl, let's think of a weak acid. So let's say you start with HF. That's the only halide that's a weak acid. If you start with that, what you're going to end up with as your salt is F minus, not Cl minus. Now, F minus is capable of changing pH, and we're going to talk about why that is. But what I want you to do for now is just focus on the product. If you're asked, for example, why is the pH at the equivalence point for a weak acid greater than 7? The correct answer is because the salt that is formed as a product is capable of changing the pH of water. How is that salt capable of changing the pH of water? Well, if it's the conjugate base, this is actually a conjugate base of the original weak acid, just using the right vocabulary, that is capable of reacting with water because it's from a weak acid. Only conjugate bases from a weak acid can change the pH of water. Because look at the reaction. If you add that to water, what do you make? You make the original hydrofluoric acid, but you also make some hydroxide. That makes the solution, the hydroxide, presence of hydroxide is going to make the solution basic. This is actually an equilibrium. Now, let's look back at when we titrated a strong acid to better understand why the product, the conjugate base from a strong acid, does not affect the pH. So let's say our sample strong acid that we are titrating is hydrochloric. And so let's go through the same exercise as we did for fluoride. If chloride were to react with water, what would we make? We would make hydrochloric acid and some hydroxide. So you might look at that and go, wait a minute, why doesn't this one make this solution basic? Because that reaction cannot occur. What is the definition of a strong acid? It is something that exists 100% in the dissociated form in water. So in other words, this does not exist. Okay, the intact strong acid molecule does not exist in aqueous solution. So this reaction will never happen, which means if the conjugate base is from a strong acid, the pH will always be just 7 at the equivalence point. In addition to the equivalence point, if you're dealing with a weak acid titration, there's another really important point that you need to be able to identify. And that is called the halfway point. Okay, the halfway point. What do we mean when we say halfway point? You should, if you've completed your KA lab, that was in there. The halfway point, so let's say that the volume of base added to each equivalence point is 20 milliliters. That means that the halfway point would be whatever the pH is at half of the volume needed to reach the equivalence point. So if you want to find the pH at the halfway point, you just calculate half the volume, go up to that point on the curve and move over to the y-axis, and you'll find the pH at the halfway point. Well, why that pH? Why is the pH important at the halfway point? Because at the halfway point, pH equals pKa. That's another thing that would be worth writing down. I hope that you have a separate piece of paper that you are writing formulas that will come in handy for the final exam and actually for exam 4. Okay, so when you've had professors in the past or teachers in the past that have told you you can have one page of formula or notes or one note card of that, that's something you want to start putting together now. All right, why is pH equal to pKa at the halfway point? Let's look at the Henderson-Hasselbalch equation. Now, as I will explain in a minute, as you start titrating, this is only for titration of a weak acid, during the titration, before the equivalence point, you actually have created a buffer. And hopefully you remember, anytime you have a buffer, you are going to use the Henderson-Hasselbalch equation. And that's another equation you want to jot down and have handy, okay? Now, at the halfway point, the concentration of the original weak acid equals the concentration of the conjugate base form, okay? That's true at the halfway point. In other words, you've titrated, at the halfway point, you have titrated or neutralized half of the original weak acid. Sorry about the dog barking there. All right, so then looking at the Henderson-Hasselbalch, when the concentration of the original weak acid and its conjugate base are equal to each other, this ratio becomes 1. A log of 1 is 0, and so pH then becomes pKa. That's a really common question to ask. So be prepared to find pKa from a titration curve. So the buffer region, as I kind of said in words on the last slide, if you're titrating a weak acid, is this entire region. As soon as you start the titration up until before the equivalence point, this whole region, you want to be able to use the Henderson-Hasselbalch equation to find pH. So whereas if we were titrating a strong acid, you simply found the pH directly from minus log of concentration. Okay, if you're titrating a weak acid, it's not that straightforward. You got to use Henderson-Hasselbalch. And so what makes titration of a weak acid so much more complex than titration of a strong acid is you don't always use the same formula to find pH like you do with a strong acid. So this is where it gets real complex if you want to take a break or take notes or whatever. So in the very beginning, before you add any base, what do you have present? All you have in the very beginning, before you start to titrate, is a weak acid and water. We know, hopefully, that a weak acid doesn't dissociate completely in water, but we know that we're going to make some hydroxide and some conjugate base, but it's not going to be complete. There is going to be an equilibrium, And so how do you, going back to when we learned about acids and bases a few weeks ago, how do you find the pH from a weak acid? Because you don't know how much hydronium ion you have formed. That is when you have to set up an ice table. And you have to know the Ka of HA. So if you're dealing with a weak acid and you're at the very beginning, you haven't added any base, you simply treat it like a weak acid ice table problem. Once you start adding base, here's the reaction that's going on. So be careful, because when you haven't added any base, the other reactant is simply water. When you start adding base, the reactant is no longer water, it's hydroxide. Or if you're more comfortable, you can write it out as NaOH. But the bottom line is this has entered the buffer region. So you have some original weak acid and you have some of its base. And anytime you have substantial amounts of the original weak acid and its conjugate base, you now have a buffer. And so in the buffer region, again, you are going to use the Henderson-Hasselbalch equation to find pH. And that's the most common type of calculation for titration of weak acid. All right. At the equivalence point, and I'm going to go through each of these steps individually, but I'm just giving you an overview. At the equivalence point, so what do we have? I'm going to write down our titration reaction again. But at the equivalence point, all of the original weak acid and hydroxide, they've neutralized each other. So the reactants are all gone, as always, at the equivalence point. All you have left at the equivalence point are the products. And so how do we find the pH at this point? We know it's not 7 for a weak acid. Well, we have to figure out how much this A-, this conjugate base, is going to change the pH. So at the equivalence point is the biggest pain to find pH, because you have to write out 2 reactions. One showing that you've reached the equivalence point, that the original material is gone, and then you have to write another reaction to show how this conjugate base is going to affect the pH. Now this is an important step, because this shows that you know this conjugate base is going to produce some hydroxide in the aqueous solution. The question is, in order to find pH, you need to know how much hydroxide. And in order to know how much hydroxide, you have to know how much of this conjugate base is going to react. Not all of it's going to react, okay? It's weak. You've got an equilibrium. So at the equivalence point, so wait a minute. In the beginning, we had an ice table for an acid. At the equivalence point, you have an ice table again, ice table problem, but it's for a base. Okay, it's for A-. And this equilibrium. Set up an ice table. X is going to equal the concentration of hydroxide, and you use that to find the pH. Now, it's not as likely at all that you're going to have a problem where you've overshot the equivalence point. But if you do, you need to know how to calculate pH. If you overshoot the equivalence point, what is going to be present in your solution? So this is what it's going to look like from a chemical reaction point of view. Okay, that's my dog again. She's getting restless. So overshot the equivalence point. Again, the reactants are going to be all gone. But now, well, no, they aren't going to be all gone, sorry. You have some leftover or excess hydroxide that didn't react. So at this point, what you have left is not only the conjugate base that you've made, but you also have some excess hydroxide. Now, the excess hydroxide is much more potent as far as changing the pH than the conjugate base. So at this point, as long as there's hydroxide present, the conjugate base doesn't even matter. So you find the pH if you overshoot the equivalence point simply from the excess hydroxide. That's going to be the only key determinant for pH. All right, that's a lot of information, but I'd just like to give you an overview before we start doing it stepwise. I'm going to walk you through a calculation at each point in the titration of a weak acid. So we're going to use the same initial volume and molarity as we did to titrate the strong acid, HCl. But now the acid we're titrating is acetic acid. And even if you didn't have your list of strong acids and strong bases, if you're given a Ka value in a titration problem, that's a real strong indicator that you're dealing with a weak acid, right? Because strong acids, they're not going to give you a Ka for strong acids. All right, so this problem says calculate the pH after addition of 0. Remember, there's no NaOH added, so all you have, I'm going to call acetic acid HA just to make it doesn't matter what the structure is. All weak acids are going to react the same way. And so if there's 0 milliliters, there is no sodium hydroxide added yet. So that's the beginning of the titration, and so all you have is water. And so you have a weak acid equilibrium. Okay, so this is when you need the ice table to figure out how much hydroxide has been formed. I probably should have had this slide before the one I just went over. This is a summary of how you find pH at every step of a weak acid titration. This might be a good slide to either take good notes on or print it out. Alrighty, before titration, so this is no sodium hydroxide added. This is a typical ice table for a weak acid. So one of the reasons that I like titration of a weak acid is it's really a review problem of everything we've learned in the last several weeks. It's very good practice to do this type of problem. All right, so simple ice table. And again, you don't have to write out the structure of the weak acid. It's perfectly fine to just write out what I'm doing right now. So you don't need to waste your time on trying to get the structures correct. All right, we are starting with ice table. We're back at concentrations, not moles, okay? So as always, initial moles of the product is 0 unless you're told otherwise. Use your handy dandy X's. Pay attention to stoichiometry. I think almost all these titrations are going to be 1 to 1 to 1. All right, and then once you have the equilibrium concentrations of everything, you go ahead and plug into Ka. So remember, Ka is products over reactants, and they will always have to give you the Ka value. And so if you plug in the concentrations at equilibrium, what do you get? Well, H3O and A minus are both X. And the bottom, the equilibrium concentration of the original weak acid is 0.10 minus X. Go ahead and neglect X. On all of my exams, you're going to be able to neglect X. But in showing your work, you have got to actually say why you neglect it. You got to say that you do and why. Neglect X because Ka is small, so you're not going to make very much X. All right, and then simply solve for X. What is X going to be? X will be the hydronium ion concentration. So if you take minus log of that hydronium ion concentration, you get the pH. So this is the pH at the beginning before any sodium hydroxide has been added. Moving on. As soon as you start adding sodium hydroxide or the titrant to a weak acid, you've created a buffer. Okay, so as soon as you've added any hydroxide at all to that weak acid, you have created a buffer because now you have the original weak acid, which I'll just call HA, and you have its conjugate base. And again, anytime you have both a weak acid and its conjugate base, you have a buffer. My dog is singing to you in the background. She's whining. All right, so if you have a buffer, if you're in the buffer region of a titration, I want to remind you now it is a two-step calculation. So it is not simply an ice table and solving for x as it was before the titration. Now it's a two-step calculation where the first is you have to use stoichiometry to figure out moles. So I'll just call that a mole table. And then the second part of the defined pH is the Henderson-Hasselbalch equation. So here is the mole table. And you're going to have to calculate moles of everything. So remember to get, if you're dealing with a solution, that moles of any substance is going to be the volume, liters, times molarity. Okay, so you're basically going to be multiplying liters times molarity to get moles of the original weak acid and moles of the hydroxide that has been added. So, for example, the moles of sodium hydroxide that have been added at this point are 10 milliliters. And so you can either use, if you're more comfortable, just moles, convert the milliliters to liters and multiply it by molarity. All right, so that would be 0.001 moles. Now, what you'll see in a lot of titrations is you will see chemists that use millimoles instead of moles. Either one's perfectly fine. Millimoles allows you to use a shortcut if you're comfortable with that, and it'll save you time. If you're not, just don't even worry about it. But millimole is basically, instead of converting to liters, you can leave milliliters. So, because titrations are almost always in milliliters. So if you multiply milliliters times concentration, you get, instead of getting moles, you get millimoles. Okay, so again, just, you don't have to, you can do it either way. All right, so in a titration, the hydroxide is going to completely react. All of it's going to react. So however much you've added is all going to react, and you're going to end up with 0 of the hydroxide left, unless you have overshot the equivalence point. So you take however much of hydroxide you've added, and that's how much is going to react with the original weak acid. Do your math, and so what you have left at this point is 4 millimoles, or 0.004 moles of the original acid left. And now if you're in the buffer region, it's not enough to just calculate the amount of acid left. You also have to calculate how much of its conjugate base you've made. Because remember, you're going to use Henderson-Hasselbalch equation, so you need both of these. All right, and that's determined by your x values in the change row. So because the stoichiometry is all 1 to 1 to 1, your original moles of the weak acid is going to go down by 1, and it's going to be plus that amount for the conjugate base. So now we have the moles of both the conjugate base and the original weak acid, and now we're going to plug those values into the Henderson-Hasselbalch equation. All right, just to remind you, those are the mole values for the Henderson-Hasselbalch equation. Remember, the base goes on top always, acid on bottom. And in this problem, they'll always have to give you Ka. So the base, typically one with a negative charge, right, goes on top, and the acid on bottom. And just kind of reminders, another formula you should write down. pKa is minus log of the given Ka value. So this is calculating pKa. So the pH at this point was 4.14. That's after you add 10 milliliters of sodium hydroxide. So just a reminder, the pH in the beginning before we added any hydroxide is 2.87. It's a good idea not to forget your common sense when you're doing these problems, okay? As you add more and more sodium hydroxide, your pH better go up with each step. Alrighty, now let's talk about how you calculate the pH at the equivalence point. This is the most complicated one. So at the equivalence point, what do we have? At the equivalence point, all of the original weak acid has been neutralized. So this is all gone at the equivalence point, and all we have left is this, okay, the conjugate base. And remember, the conjugate base from a weak acid is capable of changing the pH, of making the pH basic. So our goal at the equivalence point is to find the concentration of the conjugate base and then determine what that's going to do to the pH. So it's going to be an ice table again at the equivalence point. You had an ice table at the beginning before any sodium hydroxide was added. But in the beginning, it was an ice table for the weak acid because that's all we had present. At the equivalence point, all we have present is a conjugate base. So now we need an ice table for a weak base. And anytime you're dealing with a base, instead of Ka, you need Kb. So do you remember how to get Kb? Kb is going to equal 1 times 10 to the minus 14. Here's another equation for you to write down, divided by Ka. Alrighty. I didn't really need this slide, did I? Let's move on. All right, here we go. So, all we have left, again, is the conjugate base. So, again, you don't have to write the structure. You could just put A minus, and this would be HA. Now, as with any weak base, equilibrium in water, you're going to be producing hydroxide, not hydronium ion, okay? So at the end, X is going to equal the concentration of hydroxide. And so you're going to have to find POH first and then pH. Again, anytime you have ice table, you are dealing with concentrations, not moles. The only reason we use a mole table in the buffer region is because it's stoichiometry. There's reaction stoichiometry going on and you need moles. All right, so what is our original initial concentration of the weak or the conjugate base? Well, we have 0.005 moles. So however many moles you had of the original weak acid, it was 0.005 moles. If you go back to the original problem, multiply molarity of the weak acid times the volume, you'll see that there are 0.005 moles of the original weak acid. And since all of that weak acid has been converted to its conjugate base, you're going to have the same number of moles of the conjugate base. Now, to get concentration, you have to divide by total volume. And because remember, during a titration, the volume is changing constantly. So you need to divide by the volume of weak acid you had to begin with, and then the volume of added base. And that's always the case in a titration. Be careful with volume, and it's always total volume. All right, so we are looking at now the equilibrium of a weak base in water. And so we have to use X because we don't know how much hydroxide is going to be formed. We're going to be relying on Kb to figure that out. We can go ahead and neglect X again because Kb, I guarantee you, is going to be really, really small. So calculating Kb, again, it's 1 times 10 to the minus 14 divided by Ka. So of course KB is very, very small, which means it's very safe to neglect X. So putting in the equilibrium values from our ICE table, we've neglected X, remember? And setting them equal to KB, not Ka. We solve for X. Remember, X for a base is hydroxide concentration. So you have to find the POH first. And then 14 minus POH is going to give you pH. So pH at the equivalence point, because that's where we're at now, is greater than 7. In this case, it's 8.72. All right, final calculation. Phew. If we overshoot the equivalence point, if you add too much base, the key player is going to be the excess hydroxide. At this point, hydroxide is so much a stronger base than the conjugate base that was formed from the titration. It's so much stronger that you can essentially ignore the effect of the conjugate base changing the pH and focus just on the concentration of hydroxide that's excess. So you have to calculate the excess hydroxide. So here's a sample, okay? You had 0.005 moles of the original weak acid. And so you have excess sodium hydroxide, and you have now added 0.0051 moles of hydroxide. All right, so you are going to have 0.0001 excess sodium hydroxide. I think I show it in more detail in the next one. Yeah, here we go. But I have it in millimoles instead of moles. Moles would be fine too. So at the end, you see the original weak acid's gone. It's been all neutralized. And of course, you do have however many moles or millimoles of the weak acid you started with. You're going to have that same number of moles of the conjugate base when you've neutralized it all. But again, if you have excess hydroxide, this conjugate base doesn't matter anymore. It changes the pH a whole lot less than hydroxide. So now we just have to find the concentration of hydroxide in order to get the pH. So as always, concentration is moles divided by the total volume. Again, be careful because your total volume is 50 milliliters from the acid plus 51 milliliters from the base. So your total volume is 101 milliliters. That's where this comes from. All right, so here's the concentration of the excess hydroxide, which means POH is 3 and pH is 11. I am not going to go through the process of a weak base titration, but this will likely be a bonus type question on exam 4. So you may want to go through this process yourself. And if you do, here are the correct answers. And if you feel overwhelmed, like you have enough difficult problems to work on, which is the case with this unit, I completely understand, then you can ignore weak base titration. That is it for the PowerPoint on titrations.